Welcome, guys. Yeah, so today let's talk about the important topic in the analysis, in the continuous part. So basically, what I'm trying to discuss in this video basically is the compact and the continuous. So this is the important part in the real analysis. So I should say the undergrad analysis. So basically, we will prove that some theorem introduced in the calculus. So the most important part should be, so if a continuous function on a compact set, map on a compact set, so let's say x is compact, then f of x has maximum and minimum, and a minimum. Okay, so this is the calculus like to use. Okay, or basically. Yeah, so this is why we'll be trying to prove. Okay, so the most important theorem. So if x mapped to y, which is a metric space, and then continuous, f is continuous. Okay, so I think you can, actually in this proof that you can assume that x and y are basically general topological space, and such that let's say you get some E subset, which E is compact. Then f of x, f of e as a set is compact. So continuous function map compact sets to compact set. Okay. So quickly see a proof. Let's say we get some v alpha, which is open cover of f of e, right? So this is simple, right? Just f of e, and then there's a finite subcover because not so f of v alpha is open cover of e, right? But okay, so but we notice, so let's see. So what we are just saying that as f of e, right? It's just a open cover, right? So union of v alpha. Okay, and notice that by our assumption, right, f inverse v alpha, right, is open because f is continuous. So that means e, if we take so f of e is subset of these, right? So e is a subset of f inverse v alpha, right? But f of v and also f of inverse v alpha is open, so this f of inverse v alpha forms open cover of e. So by the compactness, since e is compact, we can pick the finite, right? So there's a finite alpha such that alpha maybe 1 to, let's say alpha 1 to n, f inverse v alpha, right? Which is cover e, right? And then now we take f, right? So we get f of e is less than or equal to alpha 1 and f inverse v alpha. Okay, so the elementary set theory will tell you that f inverse x or less than x, so it is less than v alpha. Okay, so union of alpha 1 to n, right? So now fe has the finite covering. Okay, so for any finite cover, for any open cover v alpha of fe, you can always find a subcover, right? So which tell you that finite subcover which tell you that f of e is compact. Okay, so the corollary. So let's talk about the fact. Okay, so the fact is that since f of e is compact, right? So that means f of e is bounded and closed. Okay, so since it's closed, right? So f of e contains maximum and the minimum. Okay, so a maximum can be defined to be the sup x belongs to let's say. So now let's assume that f e map into rk, maybe map into r, right? So I can define x belongs to e, which f of e, sorry, f of x. Sorry, I can define f of e, right? As a set, I can take the sup, also a minimum as inf, right? And f of e. Okay, so basically, there exists alpha such that f alpha equals to larger m, and there exists beta such that f of beta equals to small m. Okay, so this is basically all come from this compact compact notion. Okay. Okay. So another theorem, which in the routine is 4.17, which is just say that if F is 1-to-1, one map of the compact space of, let's say, compact X. So X is compact matrix space to Y. Then there exists the inverse map F inverse defined to be F inverse F of X. Right. So F of X is a point here, right? So F inverse defined to be F inverse F of X. Map X, right, is a continuous mapping. Okay, so this theorem just say that if F is continuous and 1-1 on a compact space, then the inverse is also continuous. Okay, so actually, I guess you can show that in general, if your F is continuous, some space which is non-compact, then you are not guaranteed that if inverse is compact. Actually, you are not guaranteed that F inverse is continuous. But when you are continuous and uncompact, then you're also always continuous. And this 1-to-1 just ensure that F inverse exists. Right. So you can, if you only take the subsets F of X as your codomain, then this is automatically onto, right? So there F inverse can define in this region. Okay. So proof. So proof is that we can use our previous theorem, right? So our previous theorem, you want to prove is continuous, right? So what you're trying to prove is that so remember that we proved that if F is continuous, that means if only for all the open sets V, F inverse V is open, right? So if V is open, F inverse must be open, right? So now you apply F as F inverse, right? So you apply F as F inverse. So we just show that you just need to prove. So you just need to prove for all V is open, your F V is open, right? F V is open. So V is open in X, right? And F of V is open in Y. So our goal is to prove whenever V is open in X, then the mapping is open. So this is in mathematics, this is called open map. So map open to open. So our goal is to show that F is open map. Okay. Okay, so the reason is that if V is open, by definition, the V complement is closed, right? But the V is in the subset of compact. So there is a theorem says that closed subset of compact set is compact. So what we just prove, or we just prove in my previous long video. So closed subset of compact set is compact. So this shows that the V of C is compact. Okay, so since V of C is compact, right? So by our theorem, the FV of C is compact. Okay, but which means that F of V of C is closed. And F of V of C just F of V and then take a C, right? So which show that F of C is open, F of V is open. Done. Okay. Okay, so now let's talk about another topic called uniformly continuous. So let's see. So suppose F is a function from two matrix space from X to Y, and we say that F definition, right? So we say F is uniform continuous. If for every epsilon greater than 0, there exists delta greater than 0 whenever X and Y, the distance of X and Y less than delta. So this is the distance in X. We have dy f of X, f of Y less than epsilon. Okay, so remember this delta is uniform. So that means this delta do not depend on X and Y. Okay, do not depend on x and y. This is called uniform and continuous. Okay, and this is a good exercise for you to prove that, for example, if f is mapped to R, and f of x is just x squared, then this is not uniform continuous. Not okay. So easy. This is an exercise, good exercise for you to check. Okay, so that means the uniform continuous is not trivial, even f is continuous. Okay, so if f is continuous, it's not definitely that this is uniform continuous. So even for a simple function, that this will not definitely imply. Okay, so the theorem in the undergraduate analysis that we will usually prove the following. So if f is uniformly continuous, sorry, f is continuous on a compact set, on compact metric space X, then f is uniform continuous. Okay, so actually the key idea is that the continuous is not enough to imply uniform and continuous, but if you add on compact sets, then everything will be fine. Okay. Okay, so let's see a proof. Let me see how to prove. Okay, so let's say you given epsilon greater than 0, right? So f is continuous, right? F is continuous. So what? So that means right, for each p belongs to x, let's say there is a positive number 5p. 5p is a positive number, such that when q for all q belongs to x, the dx pq less than 5p will implies that dy f of p f of q less than epsilon divided by 2. Okay, so why this is true, right? Because p is continuous, right? So for every p, right, there always exists some delta, right, which is dependent on phi of p, such that when q, so you should view q try to approach to p, right? So since p is continuous at every point x, so when q approach to p, for any q distance less than phi of p, actually you can view it as delta, right? The dy will less than epsilon divided by 2, right? For each p, you always have this. Okay, I think you know the trick, right? So now since it's compact, right, so we can find a finite guy to cover it. Okay. Okay, so let's say you can define J of P, which is all the Q satisfy this property. So Q belongs to X such that dx PQ less than, let's say, 5P divided by 2. Okay. Okay, so all the P belongs to, so this is the open, right? This is open set. So all the P belongs to X become an open cover, which cover original space X, right? So it's open cover because each guy is open. So the old trick, right? There's a finite subcover. So take, since X is compact, so take finite subcover. Okay, so once you get finite subcover, right, you can take X to be JP1 union JP2 union JPN, right? So then you take delta, right? So delta to be a half, minimum to be 5P1, 5P2, 5Pn. Okay, so the rest is just trivial, right? So the rest is just now for every q, for any pq belongs to x. So now we take any 2 points pq in x, and then let's say dx pq less than delta, right? Then by definition, then by definition, dx pq less than delta, right? But definition, this guy, right, cover x, right? So there exists m such that p belongs to j of pm, right? So p belongs to some points which jpm. So your dx p pm well less than half of 5pm, right? This is definition of jm. Okay, so and you also have, let's say you have dx qpm is less or equals to dxp, sorry, dq let's see, dpq, right? So plus dppn, right? So dpq is less than let's say this is x, right? This is x less than delta plus what? Plus a half of 5 p.m., right? So it's less or equal to 5 p.m. Okay, so now dxqpn is less or equal to 5 p.m., right? But this shows what? This shows that dy f of p f of q, we now need to bound this guy, right? Less or equal to dy f of p f of pm plus dy f of pm and f of q. Okay, so this guy, right? dfp fpm by definition, right? This df of p fpn will what? df fpn. By definition, df fpn is less or equal to a half, right? Epsilon divided by 2. Now dfpn plus fq, right? By this guy, also less than epsilon divided by 2. So their addition is epsilon, right? So what we have shown is that since we have shown is that there is a ball J condition here, right? So you use, so now your P is restricted to less than this, right? So that means any, so dx ppn less than this, so dx qpm will less or equal to 5 pm, right? So by definition, if your dx pq less than 5 of p, where p and p, then you're less than epsilon, right? So if this is pq, this is pq, right? So this guy is qpm, which is a qpn, right? So these guys less than epsilon divided by 2, and then the previous guy is f of p and f of pn. So that's right, but f of p and pn also less than half of 5 pn, which is less than 5 pn, right? So which tell you that these two conditions, using the previous this definition, you will generate 2 epsilon divided by 2. So there's some will be epsilon. Yeah, so this, while this is correct, this is this, and this is this. Okay, so another theorem. Time for finish this video. Okay, yeah, time for, okay, so theorem just say that we just show that compact is necessary. So I want to show that if E is compact set in a non-compact set in R1, then the A, there exists a continuous function f on E mapped to R1 is non-bounded. It's unbounded. Okay, so I think I haven't mentioned bounded, right? Bounded means that your there exists m greater than 0 such that f of x bounded by n for all x belongs to E. This is called bounded. Okay, and then we just show that if E is compact, then the f map into compact. So compact is bounded, right? So I want to show that continuous, the compact is really very important. If you do not have compact sets, then the f, even though if it's continuous, then the map can be unbounded. Okay, and then there exists a continuous function, also continuous function, and the bounded. Okay, but no maximum. But the f of E no maximum. Okay, so that means if you add the bounded condition is not enough. If they are not on the compact C. Okay, so suppose you add a condition such that E is bounded. So if you add a condition that E is bounded, then there is this still exists some f which is continuous but not uniform. So which means that the compact is really necessary in all these statements. If you do not have compact, then all these good property and the good theorem that we prove, most all of them fail. Okay, so A is proof. So A is really simple, right? So A says that we just sum continuous is unbounded. This is very simple. We just take out f of x is 1 over x and define f to be the open interval 0, 1 mapped to R, right? So trivial because I do not touch 0, right? So this guy is continuous at every point, but this which is unbounded because when I approach to 0, I can be arbitrarily large. Okay, so B said that f is continuous and bounded, and we need to prove that f of no maximum. So the idea is close, right? So idea is to, the close. So let's say I can define f of x to be again 1 plus 1 divided by 1 plus x squared. But I define f approach to let's see, approach to let's say 0, 1. So this guy is non-compact, right? Map to R, right? So you see, the minimum, sorry, I guess it's this. Sorry, okay. So the maximum is at x equals to 0, right? Because you can easily prove that f of x less than 1, right? For all x greater than 0, right? But x equals 0, which is 1. But the things I do not touch 0 point, right? So there's no way that there's no maximum, because I can infinite approach. I can approach 0 arbitrarily small, right? So f of x will approach to 1 arbitrarily close, but you always cannot touch 1. So f does not have maximum. Okay, how about C? So C, let's say E, right? Just pick out the same space, and define H to be X. Let's say define F to be X squared 1 plus X squared. Okay, I want to show, so now E is bounded, right? And also F is continuous, but I want to show that these guys are not uniformly continuous. Okay, so how to do this? So now, so what is super F, right? So F, when F can, when X really close to Z, 1, right? So we should, I think it's, let's see. Let's see. Yeah, so C, this C, yeah, C, so C is bounded, and there is this continuous function such as not uniform. Yeah, so C is a little bit difficult. Yeah, C will be a little bit difficult, I think. So yeah, so let me find the C in the next video. Okay, I will try to find C. I need to think a little bit. Okay, so let's go to some final example. Okay, so final example also maybe maybe this is a good example for C, I guess. So if x is 0 to 2 pi, and then you can define f of x to be cosine sine, right? So which f map to the interval 0 to pi to the r squared. Okay, so this is a unit circle, right? Okay, so f is continuous, except for this point, right? For the two, when you approach to 0, then there's a gap that you change. Okay, so which tell you that in this case f is still continuous, right? But the inverse do not exist, right? So f is continuous, right? But so sorry, f is continuous, right? Because you always map to you approach to 0 to 2 pi go to 0, which f is still continuous because this is still on a circle, right? But f inverse does not, right? So this is a theorem that we just proved that if you are in a compact space, then f inverse can be, right? But now it does not, right? Because f inverse of there is a gap here, right? So your 1, 0 is f0, right? But so if you are very close to here, then your f inverse will become approach to 0. But if your point here, then your f inverse is close to 2 pi, so which cannot be continuous, right? Yeah, so this is the idea that why the compact is also the compact. So x, the reason is that the x is non-compact. Okay, so this is why all the theorem that we prove now here this video always need to be compact. Okay, so if you compact, then you have maximum. If you compact, then you can have uniform continuous. If you compact, then inverse can be continuous. So this is why compact is very important in the analysis. Okay, so yeah, I will in the next video I will give you guys an example that I just missed. Okay, so see you guys next video. Bye bye.